Hello, this is a video on uh, the series on current electricity. This is the eighth installment in that series, and today we'll be dealing with the Kirchhoff's voltage law after we had ended the previous video with Kirchhoff's current law. So we'll be continuing with Kirchhoff's law, that is the second law, which is the Kirchhoff's voltage law, KVL, Kirchhoff's voltage law, and that is also known as the loop law, just like the case where the current law KCL was known as the junction law. This is known as the loop law. And in this law, what we have is that we will be first drawing the circuit, and the circuit that I'll be drawing over here, it will be a combination of everything. This is just to show you all the possibilities that can occur in a circuit and all the possibilities that we can consider while considering the KVL, Kirchhoff's voltage law, or the loop law. Now, there are simplified circuits in books that you may be referring, but this is one of my favorite circuits, which consists of all the possibilities that we can consider for a particular loop. Now, this is a loop, and it's a part of a circuit. So I'll be showing the extensions over here. The extensions are the ones that continue after these nodal points that we have. These dots that I can say are the nodal points over there, and we just continue with the other node that is present on the other side like this. And the resistance over here, let it be R1, which is represented externally, the external resistance. uh, then the other wire, which is vertically downward, that supposedly has a resistance R2, and again it is extending to a certain to the circuit. uh, but again here we have another node, and plus we add a cell over here and an associated resistance with this line of the wire. Then again this EMF of this cell, let it be equal to E1. The resistance over here is R3, and then again we consider another internal resistance, supposedly R4, which is associated with another cell that is present over here that has an EMF of E2, and that again is connected to the rest of the circuit at this node. Now the nodes that I have represented over here, let me just name them. I have the point A, the other point is B, and remember the extensions that I'm showing, that tells us that this is just a part of a bigger circuit. The circuit may continue outside the loop. We have considered the loop only, uh, and from the circuit, why I'm considering a completely uh, extendable circuit outside this loop is because I'll be taking different values of current through different wires, uh, which we'll be observing shortly. So the points A and B, then the third point over here is C. I name another point at the point of the cell, I name it as D, while the other point is at the node E, and then I take another point near the cell with EMF E2. I name that point as F. So we have a loop. If taken in the clockwise sense, we have it as the loop to be equal to, or to be said as A, B, C, D, E, F, and back to A. So this is my loop A, B, C, D, E, F and back to A. That is the loop. And what does the loop law state? The loop law states that the net potential difference, the statement in this case is that the net potential difference across a given loop has to be equal to 0. That is what we know as the loop law. In the previous case, when we had the junction law, the net current associated with a junction was 0. Here in the Kirchhoff's voltage law or the loop law, the net potential difference that is associated with a closed loop, as in this case the loop being A, B, C, D, E, F, A, that completes the loop, over that closed loop the net potential difference has to be equal to 0. Let's just see what sign conventions we can consider, like the case we had, like in the case in the previous case that we had considered, with the current entering taken as positive and the current leaving the junction taken as negative. Here also we can consider a certain sign convention for the potential difference between 2 points. Now, as far as the currents across the circuit is concerned, the first wire, that is AB, is carrying a current I1. Then again, because of the extensions available, the current may get added or subtracted, and in the second arm or the second segment from B to C, let us have the current in the downward direction, that is from B towards C, and the current in that case, let that be equal to I2. While the current across the wire CDE, that being I3, taken from the sense CD towards E, and finally we take, or we have a current I4 to be running downward from A towards F and finally towards E, and that is exactly in that line, along that line, that is AFE. That is quite opposite to the sense of the rest of the currents that have been considered in the other segments. Like I said, that this loop has extensions. That means the currents somewhere are getting added, somewhere they may get subtracted, somewhere they may be directed in a sense, in a clockwise sense, and somewhere, like in case of the current I4, they may be getting added or subtracted, and finally we have an I4 current to be flowing in the downward direction or in the counterclockwise sense. Now all this can be a possibility, and that is what we have considered. So now, as we can move over to the sign convention, let me just make it clear about what we can take in this case. What we can do is that as the current moves across a wire, we know that it is flowing from a higher potential to a lower potential. So obviously, if in the first wire itself, AB, if the current is flowing towards the right of your screen that you're observing, I1, that is, it is flowing towards the right, that means obviously the left end of the wire is at a higher potential, while the right end of the wire is at lower potential. Now as the current flows from the higher to the lower potential, the resistance across the wire, that can multiply with the current to give the potential difference across the length of the wire. That is, the potential difference across the length AB or across the segment AB is simply equal to the potential drop that is observed over there, potential drop as in case of the current multiplied with the resistance in that case. So what we have over here is that we are taking the potential drop as positive, and we are taking the other way around, we call it the potential gain. Supposedly the potential gain can be taken as negative. Potential gain meaning that when, and obviously this is according to our sense in which we have considered the loop. The loop that we have considered, if you remember, as I've written over there, is in a clockwise sense that we have considered. We can, however, take it in the counterclockwise sense. There's no problem with that. But here we have taken it in the clockwise sense. Now, as one moves along the loop, if you observe, whenever we are moving from the plus sign towards the minus sign, we will be having a drop, because plus is for higher, negative is for the lower. So from the higher towards the lower, we can say if there is a drop in potential, or we are dropping across the obviously it is the potential, higher potential and lower potential, so there is a drop in potential. And if in our sense that we have taken, and we are somewhere in the circuit, we are moving from the positive end, from the negative end towards the positive end, then we are considering the gain, because the negative end is the lower potential while the positive end is at the higher potential. Just for example, the case where we have the EMF. Now the EMF E1 for the cell, because we are moving in the clockwise sense, so while moving in the clockwise sense, we move from C towards D, and while moving from C towards D, obviously the smaller bar that you're observing, that is at the lower potential, that is the negative end of the battery or the cell, and the other side, obviously the longer bar is the positive or the higher potential of the cell. So because when we are moving in the sense that we are from C towards D, as we move, we are moving from the lower potential, that is the smaller bar, towards the higher potential. So there is a gain in potential in that case, and that gain is what we have taken to be negative, and this is our sign convention. This is our sign convention for now. However, we, as discussed earlier in the previous case, in case of KCL, the sign conventions can be interchanged. We can take the potential drop as negative while the potential gain as positive. However, why I have used this kind of sign convention, why I prefer this kind of sign convention, will be clear to you in a few moments. Okay, let's just continue with the proceedings over here. So we have a potential difference across AB. So this is just the potential VA minus VB, and as we move along that, what we have is that is equal to I1 R1, and obviously I1 multiplied with R1 will be taken as positive in this case, because the sense that we are going in, we will be moving from the positive end towards the negative end, and hence we'll be having a potential drop over there. Then again, after that, we move from B towards C. So what is the potential difference between B and C? VB minus VC is simply equal to I2 R2, and that will also be positive as well, because the current is flowing in the downward direction. So obviously this end will be positive and the lower end will be negative, and in the sense that we are going from B towards C, we will be going from the positive end to the negative end, and hence we'll be having a drop in potential over there as well. I hope I'm making my signs clear over here. In case of any confusion, you can repeat the video once again. So VC minus VD only comprises of the cell as of now, because at the point D, within that point D, we haven't got any resistance. So for that, between the point C and D, we are only observing the cell with an EMF E1, which provides the potential difference at this point. So E1 is the potential difference. However, it will be negative because, as I had discussed earlier, the sense that we are moving in from C to D, we will be going from the lower potential to the higher potential. That means we will be gaining some potential, and the gain in potential, or the potential gain, is taken as negative. So this thing, that is E1, has to be taken as negative. Then from D to E, that is VD minus VE, is the potential difference over there. That is equal to I3 into R3. Obviously, as the current moves along that direction that we are taking, this one is the higher potential and this one has to be the lower potential. That is why the current flows in that sense, and which is also along the sense of our loop that we are considering from D to E. So this is simply equal to I3 R3. Now with that available, we move from E to F, VE minus VF, and that has to be equal to plus E2, why plus E2? Because as we are moving from E towards F, forget about the current over there, because the current, although maybe in the downward direction, but we do not have any resistance present over there, so the resistance is above that, so we are just having the potential difference in case of the cell that is available. So E2 is its EMF as well as the potential difference as of now between E and F. And obviously from E towards F we are moving from the higher potential positive end of the cell towards the negative end of the cell, from the higher to the lower. So we have a potential drop over there which is positive. And finally, Vf minus Va is the potential difference between those 2 points, and Vf minus Va, because the current is flowing in the downward direction in this case, so obviously the upper end is positive and the lower end is negative, and we are moving from the sense that we have taken from F towards A. The sense is obviously from the negative to the positive. That means we are gaining potential over here, so that means this will be minus I4 R4. This is the reason why this is my favorite circuit, because you have all the possibilities available in this circuit, and the result is quite interesting as well. As you can see on the left hand side, we have got pluses and minuses, and as if we just add them up completely, what we end up with on the left hand side is that VA is positive over here, and if I add this entire thing, we have a minus V over there, which cancels out with the plus VA. Similarly, VB minus VB cancels out, minus VC, and VC is cancelled out, so VDs cancel out, the VEs cancel out, and finally the VFs cancel out as well. With everything cancelled out, all that we have left on the left hand side is a zero. That is what the law says, that the potential difference, net potential difference across a closed loop, has to be equal to zero. Now consider the right hand side of the equation, or the equations that we have with us. With all those things added as well, what we end up with is that I1 R1 plus I2 R2 plus I3 R3. Let me write the I4 R4 term as well, but that is in minus, so minus I4 R4. And we have the EMFs then, that is minus E1 plus E2. But because there's a zero on the other side, we can just interchange those signs, but we are not concerned about each and every sign over here. We just take the EMFs onto the other side, E1 minus E2, and we keep the product of the resistance and the currents onto the right hand side, I1 R1 plus I2 R2 plus I3 R3 minus I4 R4 remains as such. With all these things available, what we finally have is that what we can say is that the sum of the EMFs, or the sum of the EMFs, net EMF across the circuit, across a loop, has to be equal to the summation of the current multiplied the product, the summation of the product of the current with its corresponding resistance. Here ix, obviously, as you know, I extends from 1 to 4, and the summation depends on the sign convention over here that we have considered. The sign convention being, in our case, that we have taken is that the positive potential, the potential drop is to be taken as positive, while the potential gain has to be taken negative. Now there's an advantage to that. uh, However, we can take it the other way around, because in the other way around, if you observe all those equations, those I think 6 equations that are present over there, these lot, the in these equations, if we had the potential gain to be positive and the potential drop to be negative, it wouldn't have really mattered to us, because with that being the case, E1 would have been positive and E2 negative, and I3, I4, sorry, I1, I2 and I3 terms would have been negative, while I4 would have been positive. But that doesn't really matter, because we end up with a 0 on the other side. So again, rearrangement will give us the same result that we have obtained as of now. So the sign conventions, although if you are taking one of them as positive, the other one will be negative for sure, but the sign convention that I have taken, I have used in this case, is more suitable in as far as I see it, because if you observe that whenever the current lies in your sense, in the sense that you consider the loop, the current multiplied with the resistance is positive. I mean, the potential drop or the potential difference, so as to say, is positive in that case, while the current which is opposite to your sense that you have taken is a negative, just like in the case of I4 multiplied with R4, because I4 is opposite to the sense that we are considering the loop with. So as we are moving from E towards F towards A, the current is moving in an opposite sense, and hence we have minus I4 R4. So we need not be worried about the potential gains or drops anymore. We just have to take the currents as positive along the direction of our sense, and we can take the current which is lying in the opposite sense of our loop consideration, that can be taken as negative. So this is an easier way considering that. Else you can choose your own sign convention, doesn't really matter. At the end you will be having the same result. So this is simply the KVL or the loop law, and there's another statement to it, as you can see, that the net EMF across a loop is equal to the equal to the sum of the product of current with with their corresponding resistances. Now this is another statement of KVL. We can say that, because in the Kirchhoff's current law we had two statements as well. Here in the KVL we have two statements as well. There in KCL we had the junction law, which stated that the net current associated with the junction is zero, and here in as we consider the loop law, the net potential difference associated with a closed loop is, or across a loop simply, is equal to zero. The loops are always closed, obviously. There in the second statement, after rearrangement, what we had is that the current entering into a junction is equal to the current leaving the junction. The total amount of current entering into the junction is equal to the total amount of current leaving it, because that followed the conservation of charge, because charge was neither created nor destroyed. Here as well, after rearranging, what we have is that the EMFs, the sum of the EMFs or the net EMF in a given loop is obviously, EMFs are the source of energy to the loop. They provide electrical energy, they provide the potential difference necessary for the functioning. Of course, this loop has external branches, extended branches, and you may not have, even if these loops didn't have any kind of EMFs in them, the source, that is, the currents would have flowed anyway, because of the extensions, the external circuit may be having some source by itself, and it may be providing current into this loop. But here we have already taken two cells with different EMFs, just to show you that this is also a possibility. And in this case, with this possibility available, what we have is that the net EMF that is available to the loop, the net EMF that is available to the loop, provides the energy for the potential differences across the various resistances that are present. And the potential differences across the various resistances present in the circuit is simply equal to the product of the resistance with its corresponding current. That is what we have obtained on the right hand side. So this is in accordance with the conservation of energy. So this is in accordance with the conservation of, obviously, electrical potential energy. We simply write it as energy. While KCL was in accordance with the conservation of charge, this is in accordance with the conservation of electrical energy. You can try many circuits that are available for numericals, and they will be solved quite easily with the Kirchhoff's laws. And this uses the KCL to some extent as well, because the currents have been branched in a way where you can use the KCL and the KVL. We will just move over to the example where we are using this KCL and KVL, and that is the Wheatstone's bridge. As I had discussed earlier, we have a Wheatstone's bridge, a particular circuit which involves the which in the balance. In order to obtain the balanced condition of that circuit, we use the Kirchhoff's current as well as the voltage laws. So let's just get along with it. In case of the Wheatstone's bridge, we have a bridging circuit. Bridging circuit comprises of the circuit that I'm going to draw right now. This is a given arm. This is another arm in the form of wire, we can say. We have two other arms. Each arm is provided with a resistance. This is more or less a square shape, but aligned in that manner. And here is the bridge carrying a galvanometer. Now, a galvanometer is a device which is used to measure the amount, which is used to measure or detect, not measure, but detect the presence of current in a circuit. Now, these arms are provided with a cell as a source of energy. So this gives a potential V, which is to provide a certain current across the circuit. And let me just name them. We have this as A, B, C, and this is point D. And the resistances across the resistances that have been provided, let them be equal to P, Q, and this is R, and this is S. Now, in this case, what we have is we can see a bridge in the form of a galvanometer from between the points B and D, and we have four resistances P, Q, R and S. We have two, three or maybe four loops. You can have as many loops as possible, but we will be considering two loops out of them. The first one being the loop A B C D A. This one A B A B sorry A B D and back to A. So this is A B D A loop. Now what we do is we start off with KCL. The current that is entering to the junction A over there gets distributed. As it gets distributed, we have two currents flowing across the two wires that are moving away from or leaving the junction A. If this one was I that has entered A, and we have I1 to be coming out of A, then from Kirchhoff's current law, obviously the rest of the current that is moving from A towards D, it has to be I minus I1, because it will be having because the sum total that is entering has to be equal to the current that is leaving. So if I1 is leaving on one end, from one end, the other end must have I minus I1, because the total current entering was I. Out of that, I1 was given from A towards B, and what is left from I minus I1 is left, which moves from A towards D. Let me just write it clearly over here. I'm just scribbling it and I'm writing it clearly over here, I minus I1. Now that current I, as it moves towards the junction B, it again gets divided, and out of that, the junction from the junction B, the galvanometer has a certain resistance. Let that resistance be equal to G itself, the capital G that we have written for galvanometer, and it draws a certain amount of current Ig supposedly towards itself. So Ig flows from B towards D through the galvanometer G, and because I1 was the current that was entering into the junction B, out of which Ig has been given has been drawn by the galvanometer, so all that we are left with is the current from B towards C has to be equal to I1 minus Ig. As simple as that. So this is I1 minus Ig. Now all we are doing here is following the Kirchhoff's current law, KCL, and as the current moves along the galvanometer bridge, that is from B towards D, it meets the current that was flowing through AD, that is through the resistance R, that is I minus I1. So both those currents, as they meet at the point D, they get added. They are entering into the circuit, so they get added, entering into the junction, so they are getting added as per the junction law over there. So they get added, and what flows through DC is simply equal to I minus I1, that was the current that was flowing from A to D, and then again what has been added to it is Ig that was flowing from B towards D. With all these currents available, they are entering the junction C now. So what is entering into C is that I minus I1 plus Ig from D, and from the point B we have I1 minus Ig. With all these currents added, what we are left with is that I minus I1 plus Ig plus I1 minus Ig. They cancel out, and all we are left with is I. You can just add these two terms, these bracketed terms, this one, and you will end up with I. So the current I that was entering over here is the current I that we are getting back, and that is in accordance with the law of conservation of charge. which satisfies the Kirchhoff's current law as well. So the distribution is quite obvious. Now consider the loop, back to the loop law. With the loop ABDA taken in the clockwise sense that I have drawn, what we can have is that VA minus VB is the potential difference across the points A and B, and that is simply equal to I1 multiplied with P, because I1 lies in the sense, along the sense that we are considering the loop. So in that case, as I had taken previously, it is simply positive, that is I1 into the resistance P. Again, as we move from B to D, VB minus VD, we have the current as IG, which is obviously along our line or along our sense, and so this will be positive as well. So IG multiplied with G being the resistance of the galvanometer over here, as I had said earlier. Now from D to A, that is VD minus VA, the current is opposite to our sense, so we can simply take that as negative. So minus of I minus I1 in brackets multiplied with the corresponding resistance R, because there is no source of EMF over here, so all these end up or give or equate to 0. This is for the loop ABDA. Now consider another loop. We have another loop over here. Let this be loop 1 and this be loop 2. So we are now considering the loop 2. This was loop 1. Now we have the loop 2. What is loop 2? BCDB. That is BCDB. That is the other loop, loop 2. And taken in the sense BCDB. From B towards C, if we observe, this is the current is in our sense, so we have I1 minus IG multiplied with Q in the positive way, and then the other current from C towards D is against our sense, so that has to be taken as negative. So I minus I1 plus IG whole multiplied with the corresponding resistance over there is S. Then again, as we move from D towards B, we have minus Ig in this case multiplied with G, and all of them add up to give 0, because there is no EMF present in that circuit whatsoever, which would have remained on the other side. Now just like we have a pointer in the galvanometer, and the pointer in the galvanometer is deflected, showing the presence of current in that circuit. Now under balanced condition, what we have is that the galvanometer must not show any deflection, which means the load is equally balanced on either side, or we can say the potential difference remains the same between the points B and D, or there is no potential difference in fact between the points B and D. So there will be no current flowing across the galvanometer, and hence it will show no deflection. So that means VB minus VD will be 0 in this case. That means VB will be having the same potential as that of D. The point B and D will remain at the same potential, which will obviously give the current across the galvanometer to be 0, and hence no deflection of the galvanometer, no deflection of the pointer, which means it is steady, or it is in balanced condition. Now how to obtain that balanced condition? With this condition available, now we are going in the reverse way. Now we have the balanced condition already, that is Ig is equal to 0. This is the balanced condition in fact, but we are to obtain the condition for that balanced condition. Now what are the conditions, what are the requirements for that balanced condition? We go back to the formulas that we have just obtained. We have Ig to be 0. Now for the first equation over here, the first equation that we had obtained that I've just ticked right now, that is for the loop ABDA. If I put IG to be 0 in loop equation ABDA, for IG being equal to 0, what we have is that I1 times of P, the second term goes to 0, and the third term is minus, which can be taken to the other side. We have I minus I1 whole multiplied with R. And in the loop equation for BCDB, for IG being equal to 0, that is for the balance, under the balance condition, what we have is that we have I1 minus IG goes to 0, so I1 is all that we have left multiplied with Q, and the third term IG is 0, so third term goes away completely. The second term has minus of bracketed I minus I1 plus IG is 0, so all we have left is the bracketed term is I minus I1, which is obviously negative in this case, can be taken to the other side, so we have I minus I1 whole multiplied with the resistance, that is S in that case. Now taking the ratio of both these equations that we have obtained, simply taking the ratio, we have I1 into P divided by I1 into Q on the left hand side, and I minus I1 into R and I minus I1 multiplied with S. The current terms can just cancel out, and all that we have left is the condition for the balanced condition is that the ratio of the resistances must be such, or the resistances must be so selected that their ratios will result in no deflection or no deflection of the galvanometer, resulting in its balanced condition. This is however much useful in case of meter bridges as well as potentiometers that we'll be discussing in the upcoming videos. We can just rearrange this formula where we have P by R is equal to Q by S. They just got cross multiplied. So that means you can take the ratio either horizontally sidewise, that I am just encircling right now in the figure, like this by this, or the vertical ratios, that is P by R has to be equal to Q by S. So it's either the horizontal ratio or the vertical ratio, whatever it is, the ratios have to be equal so as to obtain a balanced condition, which means there will be no current flowing through that bridging galvanometer that is placed in the circuit. That's all from this video. In the next video we'll be using, or we'll be considering the applications of the balanced condition of a Wheatstone's bridge, that involves meter bridge, that involves to some extent the potentiometer as well. They are the electrical equipments, or electrical equipments for measurements, for making measurements, the various types. But that is for the next video in this series. Till then, thank you for watching. Goodbye.